In this short video, we present a full and more or less self-contained proof of the spectral signatures theorem we proved in Lecture 4 of my video series on robust statistics. If you want to see more context or motivation behind anything described here, I recommend you check out that video or my lecture notes, both of which I'll link below. This theorem is about estimating the mean of a dataset when it has been corrupted by a small fraction of adversarial outliers. At a high level, it says that perturbations to the mean caused by a small fraction of outliers must necessarily result in an unnaturally large eigenvalue in the covariance. Let's make this formal. We'll let S denote our corrupted set of points, and we'll call them x1 through xn. Our corruption model, as described in the lectures, is that S can be decomposed into three parts. The good, uncorrupted part, which I'll denote Sg, the bad, added outliers, Sb, and the points removed from Sg, denoted Sr. Just remember, G for good, B for bad, and R for removed. Our conditions on these sets are that Sg is the original set of n good points, Sr is a subset of Sg, and moreover the size of Sr and Sb are epsilon times n, where epsilon is some small constant. Secondly, we'll let mu denote the empirical mean of the good points, and sigma denote the covariance of the good points. I should say, throughout this video, I'll slightly abuse notation and conflate S with the set of indices into S, and similarly for other sets. Like here, I write sum over I in Sg to mean the sum over the points in Sg, but hopefully the meaning should be pretty clear. I should also mention that all these sets should really be multisets of points, as repeat points are allowed, but let's not worry about that either, because nothing changes in the proof either way. Before we can state the theorem, we're going to need the following notation. I'm going to go over this kind of quickly, but again, if you need more context or intuition, please refer to Lecture 4 or my lecture notes. We'll let gamma sub n denote the subsimplex over endpoints, namely the set of non-negative w1 through wn, which sum up to at most 1. We'll also let w of s denote the uniform set of weights over s, namely w of s of I is equal to 1 over n for all I in 1 to n. We're going to consider reweightings of our points by weights in gamma sub n, and so for any set of weights w in gamma sub n which are not identically 0, let mu of w denote the empirical mean of our set of points weighted by w after normalizing w to have L1 mass 1, and let sigma of w be the empirical covariance of our set of points weighted by w, although here we don't renormalize. The spectral signatures theorem will talk about the following set of weights, which I'll denote script w sub n epsilon. This is a set of weights w in gamma sub n, so that the L1 distance between w and the uniform distribution over S is at most epsilon, and w sub I is at most 1 over n for all I in 1 to n. This is all the notation we'll need for this video, so don't be afraid to refer back here whenever you need to. But with this, we can now state the theorem. It says the following. For any epsilon less than 1 and w in script w sub n epsilon, we have the following inequality. I'll let you read the specifics, but morally, it says that the L2 distance between the true mean mu and the weighted mean mu of w can be upper bounded by this quantity, which depends on the spectral norms of sigma and sigma of w. In particular, if both of these spectral norms are bounded by a constant, the right-hand side is order square root epsilon. Notice that the first term on the left-hand side, the sum over I in S intersect SGWI, is lower bounded by 1 minus 2 epsilon, at least when epsilon is small. So when that happens, this term contributes a small constant factor to the bound. But the form we have is tighter, so we'll prove this statement here. The proof will proceed in a number of steps. Let delta be mu of w minus mu. We'll write the following sequence of equalities for the quantity, which is the L1 norm of w times the squared L2 norm of mu of w minus mu. First, observe that the squared L2 norm is simply mu of w minus mu in a product itself. Since delta is equal to mu of w minus mu, we can replace one of the vectors in the inner product by delta. We can then expand out the second copy of mu of w minus mu and absorb the factor of the L1 norm of w to get the following expression. We can then break up the sum as a sum over SB and the sum over S intersect SG, and we'll bound the contribution of both of these terms separately. Let's first upper bound the contribution to the sum from the terms in SB. We can add and subtract mu of w to obtain the following expression. Note that since delta is equal to mu of w minus mu, this second term simplifies. Before we bound the first term, we'll need to use the following simple fact, which follows directly from Holder's inequality. It says that for any numbers a1 through an and any w in gamma sub n, we have the square of the sum of the wiai's is at most the sum of the wi's times the sum of the wi's times ai squared. Applying this fact with a set of weights being the w restricted to SB and the ai's being delta inner product xi minus mu of w, we get the following expression. The first term on the right hand side is upper bounded by epsilon, since each wi is at most 1 over n, and SB has size at most epsilon times n. To bound the second term, notice that each summand is non-negative, and so we can only increase the sum by introducing more terms. So let's just throw in all the remaining points in S. The reason we do so is because now this expression is actually really simple. It's just delta transpose times sigma of w times delta. Finally, by the definition of spectral norm, this is upper bounded by the spectral norm of sigma of w times the L2 norm of delta squared. Taking square roots of this quantity and combining it with the previous inequality, we get the following overall bound for the contribution from the points in SB. We can upper bound the contribution from the points in S intersect SG in a very similar way. Let's first extend the definition to say that wi is equal to 0 for I in SR. Then, to bound the expression, we can add and subtract the uniform set of weights over SG. When we do so, the first term becomes 0, since mu is the mean of the good points, and so we're left with the second term. To upper bound the second term, let wi prime be the negative of the weights in the expression above. That is, wi prime is equal to 1 over n minus wi for all I in SG. It's not hard to see that the wi primes are all non-negative and sum to at most 1, so they're also in the subsimplex. Moreover, wi prime is entry-wise at most 1 over n. The fact that w prime is in the subsimplex means that to bound the square of the expression we have, we can invoke the same fact as before. We're technically squaring the negative of the expression we had, but obviously that's equivalent. When we apply that fact, we get the following expression. To bound the first term, split up the sum of the wi into the sum over S intersect SG and the sum over SR. The sum over SR is at most epsilon because SR has size epsilon times n, and each wi prime is at most 1 over n. The sum over S intersect SG is bounded by the sum over all of S, which is just the L1 norm between ws and w, which is at most epsilon since w is in script w sub n epsilon. Thus the first term is at most 2 epsilon. To bound the second term, notice that again the summands are all non-negative, and since all the wi prime are at most 1 over n, I can only increase the sum by replacing the wi prime with 1 over n. After doing so, the point is that this is now simply delta transpose times sigma times delta, which is at most the spectral norm of sigma times the L2 norm of delta squared. Taking square roots, we get the following upper bound on the original quantity. Let's put it all together. We originally had the following equality. We upper bounded the first term by this, and the second term by this. Moving the second term on the right hand side over, and cancelling a factor of the L2 norm of delta, we get the following expression. To conclude, simply observe that the L1 norm of w is simply the sum of the wi over SB plus the sum of wi over S intersect SG. So the first term on the left hand side can be rewritten as follows. Plugging in the definition of delta, we see that this is exactly the expression we wanted. This concludes the proof.